All right, well, let's just jump right in. So what I'm going to do, just as an overview, is I'm going to describe a problem for you, and then I'm going to try to solve it with your help. And then we're going to fail and just try again, okay? So imagine that we're part of a trendy sunglasses startup. We're making these really trendy glasses here. And we have a large collection of frames, actually, so we want to our designers are asking for a tool to tell if we have lenses of similar shapes. So you can see these are diamond shaped, for example. But we have a whole bunch. So some constraints, they're all convex polygons. That's because they're more trendy, and also it makes this talk a lot easier. So they're cut out of a larger lens with a gradient on it. So we want the lenses to have the gradient in the correct position. So the actual absolute position of the polygon is important here, right? So you can see these two shapes are kind of similar, but they're in a different position, so we would not want to consider them equal, okay? And also we want to have sort of an approximate equality, so we want to provide a tolerance value and somehow have some sort of a fudge factor there. We'll get into that more. So let's just give it a try. Ultimately, we're trying to write this function. That's the tolerance value as the first argument, and then two convex polygons. And we want to say, are they approximately equal? Okay, so let's start out with some simple data types here. I hope you all know what a point is. So we're representing it with two doubles. That's the x and y coordinate, x and y. So we also have a convex polygon. That's a new type, which has a list of its vertices and a little example for you. So the list isn't just an arbitrary list in any random order. They are a walk around the boundary. So you can't just have them kind of like zigzagging around. It's actually a counterclockwise walk around the boundary. Okay. So just to reiterate, it's counterclockwise. So these are some constraints that we have, or some invariants that are enforced by a smart constructor. So for the purpose of this talk, you can just assume whenever you see a convex polygon, these properties are going to hold. So another one is it's not self-intersecting. I think that's fairly self-explanatory. Another one is also that it is in fact convex. And it's very important that you understand what convex means here. So if you look up on Wikipedia, you'll see a very similar diagram. But essentially, convex means if you take any 2 points in the shape, so this one and this one, for example, and you draw a line between them, then all of those points are also inside of the set or inside of the shape. So you can see the one on the right, we pick these 2 points and we draw a line between them, but this area in the middle is not inside of the shape, so we know it's not convex. All right. Any questions so far? No? Good. So let's explore what we intuitively feel about equality. So this is going to be very interactive, so I'm going to be asking you to hold up your hands a lot. So if you think these two convex polygons, this is very easy. Do you think they are equal? Put your hand up for yes. Okay. Hand up for no. Anyone? Good. All right. A little bit more complicated. Now we have two b's in here. So we have an extra point, but it's the same as the previous one. So how do we think about it? All right, hands up for yes. They're equal. All right, pretty much everyone. Or no, they're not equal. One person. Good. A few people. Yeah, I want people to disagree a little bit. All right, how about this? We have an intermediate point now, so it's in between these two. All right. Hands up for yes, they're equal. And hands up for no. All right, great. Generally, everyone seems to be in agreement, though. And this one's a little bit more complicated. So actually, there's the same number of points in here, the same points, actually A, B, and C, but a different order. They're still in counterclockwise winding. That's something we can assume for the whole talk. But one starts from A, goes to B and C, and the other goes B, C, A, right? So A, B, C versus B, C, A. So hands up for they're equal. Everyone, and hands up for not equal. All right. Okay, sure. So let's say we just go ahead and try and implement the first thing that comes to mind, and we just directly compare the list of vertices. So this is our implementation for exact equality, not approximate equality. I think most of you will think this is a bad idea, considering everyone sort of thought the last few things were equal. Yeah, it doesn't deal with intermediate points. Sorry, that's this one. It doesn't deal with the rotated version, and doesn't deal with duplicate points. Only the very first example where they're vertex for vertex equal would work. So how can we fix this? One thing we could do is we can go into the smart constructor and we can say remove intermediate points, remove duplicate points, and then later on in the equality function we can try all rotations of the second list. And that'll deal with those three problems. Okay, and is anyone sort of confident that this is correct? Can I see hands for people that are confident? No one person, okay. I mean, I'm actually fairly sure that this is correct, but I'm kind of scared to say it because I'm not really sure, all right? But let's assume that it's correct and say, hey, can we adapt this for approximate equality now? Is there an easy way to do that? And I think the more you think about it, it's like you might be able to convince yourself one way or the other, but as soon as you come across this case, you're probably going to convince yourself that there's not really much hope in taking that sort of route. So let's look at the corner here. Given a large enough tolerance value, you might consider that all three of these points are actually approximately equal, whatever that means. So then you think about, well, what about getting rid of duplicate points? You know, we might merge these two together somehow, but then you're actually changing the shape of the polygon, and you know, it's not clear what's going to happen there. And you can say the same thing about intermediate points. You might want to get rid of intermediate points that are approximately intermediate, but yeah, again, that's going to change the shape of the polygon, so you don't really know what's going to happen there. And here's an even worse example. If we pick this tolerance value, you can see that none of the vertices are even approximately within the tolerance value from each other. These two look close, but if you've got a keen eye, that's still twice the difference, twice the tolerance value apart, plus a little extra. But if you look at the distance between each vertex and the other polygon, it's within the tolerance distance. Okay, so in this case, it's arguable that they're equal. Some of you might think they're not equal. But actually, this whole exercise is a little bit pointless because we haven't even stated what it means to be equal, and that's essentially this problem. And I'm stealing this quote right out of Connell Elliott's talk, so it's not only not right, it's not even wrong. And that means like we're not specifying what right is, so you can't say that it's wrong, right? So let's try that again, but try and apply denotational design. So I think the core of denotational design is really that you want to give a mathematical, like a precise denotation to the objects in your code. You can read that as give a mathematical meaning to the types in your code, and we'll see examples of this. And also specify all functionality in terms of those denotations. So if you have a function, take some data in, spit some data out, and you want to describe what that function does in terms of the denotation of the things it's taking in and taking out. Okay? And again, we'll see examples of that. So why do we want to do this? Well, first of all, we can say whether or not we're correct. We can say what it means to be correct. But also, it's going to guide our design. So you know, what functions are we going to even do? What are the functions going to do? That's going to help us design that. And it's also going to help the actual implementation. I'm hoping that you guys will get a good, or you're going to see that the implementation is heavily guided by this. And probably, it's probably going to be a lot simpler than you think it is. So a little bit on notation. So the way I'm going to go about it is I'm essentially going to write code comments in this form. So we're writing these box brackets, double box brackets, and in between them is some Haskell code. That is actual Haskell code that we're going to put in there. And then all the blue stuff around it is math. So our first example is a line segment. So you can see the data type there. It's represented by 2 points. And we say that the meaning of a line segment between point A and point B is this piece of math. And this is set notation. So it's a mathematical set, right? It's a set of points. Now, you don't have to understand this equation to understand the talk. You just have to know that it's a precise mathematical definition for this line segment. and that all the points in the line segment are in the set, and all of the white space around it that's not the line segment are not in the set. I think that's clear. Does anyone have a question about that? No? Yes?
You're representing there the line segment with the two endpoints that are equal. I'm guessing you wouldn't like that because that's just a point.
Yes. So
Yeah.
the question is it? Do we want to be able to express line segments with the same start and end point? Is that right? So at the moment, I haven't said anything about that. I personally would go about that with a smart constructor, not allowing that as an invariant. But it really depends on your use case, I think. Okay. Yeah, yeah. So if it was just if A and B were equal, then according to this definition, it would just be a point. You'd have a set with just a single point in it. Yeah. So you could, it works with this denotation, but you might want to disallow that just for a design reason. Yeah.
Is that an interval of real numbers or an interval of doubles?
Well, I'm pretending like it's real numbers. Yeah, sure. All right, next one, a half space. So this is just a line through space, and everything on one side of the line is in the set, and everything on the other side is not in the set. If you're paying close attention, you're probably wondering, what about the line itself? Is the line itself in the space? Well, because we're giving a clear mathematical definition, you can see that that's a less than or equal to. So by this denotation, the line itself is also included in the set. So once you start defining things so precisely, questions like this, which you might not have thought of, kind of pop up. So yeah, going through this process is important. It brings insight to your problem, I think. Just a small example. Okay, is that clear to everyone? Any questions? All right, the fun part is convex polygons. So how do we describe a convex polygon? So if we look at the equation, what I mean by that is it's the intersection of the half spaces of the vertices. So what do I mean by half spaces? I could show you a very boring mathematical description of it, but it's really easy to understand intuitively. So here we have the vertices of a polygon, and we're just going to walk along it in counterclockwise order, and we're going to look at each pair, neighboring pair, and we're going to draw a line through it and make a half space out of it. So first one is like that. And now we're taking the intersection of all these, so we draw the second one, and the darker area is the intersection so far. And we keep going until the dark space in the middle is the polygon itself. Okay?
How do you know which half space? Like you took the first 2 points.
Ah.
The half space was one of the two.
Exactly. You take 2 points, and how do you know if the half space is on the right or the left of the points, right? That's a great question. I didn't think anyone would ask that one. So I told you, so this thing, vertices, the order matters. And remember I told you there's an invariance that it's counterclockwise winding. So what you can do is actually when you're looking at the points, let's say this and this points, you know that this point comes first, and you're kind of moving in this direction, at which point you can just sort of look to the left of it. So you're always going to be looking to the left because it's counterclockwise winding. If the points were in clockwise winding, it'd be on the right side, but yeah. Okay, good question. Any other questions? Right, so you may have noticed that all of these shapes are described as point sets, right? Which is great because now we can actually write type classes, and we can describe what the type classes are or what the functions of them do according to the denotation of a set of points. Okay, so as an example, let's start with distance. And what I mean by distance is really minimum distance. And we can first define this function, distance between A and B. In this case, A and B are sets of points, is minimum. And I hope you can read that. But essentially, it's saying all points from all points in A and all points in B. That is, we're taking all the points in A and we're comparing them to all the points in B. And we're taking the point distance between them. That's just normal Euclidean distance. And we're trying to find the minimum, okay? And then we just say that this function distance has the denotation of that exact function, okay? Yeah, so Right, and here's the instance for distance between point and point. There's a small subtlety that point sometimes has two denotations, but I'm not going to get into it. It's either the point itself or a singleton set of a point, but it's clear from the context. So here's where you guys get involved. I want you to look at that for a second and think about what the distance between this singleton set of a point 0, 0 and this singleton set of a point 10, 0 is. So what is the distance? Yeah, who thinks it's 10? Great, everyone. All right, let's make it a little more challenging. So instead of a singleton set for A, we're going to make it into a polygon, and we're going to include all the points inside, just like we do for convex polygons. All right, so take a second. Who thinks it's 5? Nobody. How about 10 again? Yeah, very good, it's 10. All right, see, it's easy, right? Now this one's a little trickier. Is it 10 again this time? No? 0. Thank you. Yes, it's 0. Wonderful. You guys are getting this. All right, how about this next class? Sorry, was there a question? Why not negative? Ah, good question. Right, so look at this. The denotation that we gave it means that we're finding the minimum of point distance. Point distance is always positive, right? 0 or positive, yeah. Well, sure. Yeah, and that's a great point, actually, because if you're designing something like this, you might come up with this function, and if you weren't using denotational semantics, you might have a whole argument with someone, what does distance mean? Like, should it be negative? Should it be only 0 or greater? And once you decide on a denotation, you can actually answer that question clearly, right? I mean, it might be, and this is very possible, that you actually disagree so strongly that you have to go back and change the denotation, but that's also fine. It's part of the design process. Okay, so contains. The containment type class, well, is actually, I just give it this denotation of set containment. It's fairly simple. I think that would be a very natural denotation for everyone to give. So we're saying that A contains B if B is a subset or equal to A. Okay, and another quick quiz for you guys. Does A contain B? Is B a subset or equal to A? Yes, hands up. Yes, I tricked some of you. Okay, great. Yeah, how about now? Is B a subset or equal to A? Does A contain B? Hands up for yes? Yes, great. All right, how about now? Does A contain B? Hands up. No. Does A not contain B? Great, wonderful. Now it gets trickier. Does A contain B? Think about it for a second. All right, hands up for yes, it does. Hands up for no. This is too easy. Right, so this is another case, though, I think, where if you didn't have denotational semantics, you'd be looking at this and you might be arguing with your colleague, and they might be saying, well, A contains part of B, so I would say that A contains B in this case. But again, once you've chosen a denotation for what contains means, then this just follows from the denotation. Okay. Equality, just define it as set equality, right? It's easy. And in the second line, I've also given you an alternative example, a little bit of foreshadowing here. So you can write that the set A is equal to set B by saying like A is a subset or equal to B, and B is a subset or equal to A. Okay. So what about approximate containment, right? Now it gets a little bit trickier. So the way I decided, excuse me, that was really loud. The way I decided to implement this, or the denotation I decided to give to it, is to define this function expand, which takes a set and expands it intuitively. And by that, I mean this second part here, where we're taking all of the points in R2, that's just all the points, and we're saying, of those, look at the ones that are within the tolerance or equal to it, within or equal, excuse me, what am I saying? So the distance between that point and the set A is within the tolerance distance. Okay, so we're just kind of adding a little bit of space around it. And if that's not clear to you, this next picture will make it very clear, I think. So we have a set A, and we add the distance around it. So it's important to note that the distance between the points inside A to themselves are essentially 0. So A is included in this new set. Is there any questions? Is that clear? So when we ask, does A approximately contain B, I've kind of drawn a little tolerance value here. Then all we really need to do to answer that question is expand A and check that B is now fully contained in that. And it is, so in this case, A does approximately contain B. Okay. And from that, we can ask about approximate equality, and we can say, we had this other great definition before for equality where we said A is a subset of B and B is a subset of A. And we can just apply that here and add, this tolerance factor into it because we just defined approximate containment. Yes?
Why isn't it or rather than and?
Wasn't it what?
Why isn't it or rather than and?
Right. So if it's or, then these two would be equal, yeah? Or approximately equal.
Oh, right, okay, sorry.
Yeah. So they both need to contain each other, yeah. So yeah, when you're designing stuff like this, this was sort of the first intuition. You should then go and explore what it means, really, and I think it's actually quite a good definition. So I decided to stick with it. Oh, and I should say, yeah, the cool thing is because we have another type class for approximate containment, we can already write a default implementation using default signatures here, right? So we have a default implementation saying if you have an instance of approximate contains AA, you already can implement approximate equality, right? And just to show you an example, so in this case, we're trying to see if A and B are approximately equal. So this is what we do. On the left, we're expanding A, and we see that B is entirely inside of it. And on the other side, we expand B and see that A is also inside that. So we know that they're equal now. It should all be very simple. So if this is easy, then I've done my job well. Great. So finally, this is what we were waiting for. Sorry, it's not really. Now we're actually, going to actually go ahead and implement that, right? So I've just given you denotations and I've defined some type classes, but how do we actually implement it? And that's an important point. So here we're trying to implement contains instance for convex polygon and point. So we're saying, does a convex polygon contain a point? And what we do is we start out with this denotation here, and we just apply the denotation of contains. So really, we're just like expanding it out. So we say, polygon contains P if P is a subset or equal to polygon. And then, we say, what's the meaning of P? Well, P is just a singleton set of that point. And the meaning of polygon is the intersection of its half spaces, as I explained before. Yeah, and what does that mean? Well, it means, and this is a simple transformation here, if the point is in all the half spaces, then you can also just say that if the point is in all the half spaces, then it's in the intersection of all the half spaces. So in other words, you don't need to check that the point, you don't need to really think about the entire intersection and check that the point's in there. You can check the individual half spaces first. A little bit of set theory there. Okay, and then this thing is actually, whenever you see a for all, you might get worried about implementation because we're talking about these sets which have actually an infinite number of points in them. But in this case, we're doing a for all over the half spaces, and that is finite, right? So we can actually implement it right away. And you can see the implementation is almost a one-to-one translation of the denotation here. It's just for all the half spaces given the vertices, check that H contains P. So the point is in the half space. All right, so it's essentially one line of code split up into 4 lines. Okay. Any questions? No. All right, what about distance from point to convex polygon? Now this one gets a little trickier as well. What we do is we expand again. We're saying distance between P and polygon, and we can actually split this into 2 cases. So we can say when the point is actually inside the polygon, or is a subset or equal to the polygon, aka the polygon contains the point, then we know right away that the distance is 0. And that suits the definition of distance, as per your question before. Distance can't be negative. And if it's not inside the polygon, we can just check the distance to the boundary. And we have an instance for this as well. which I'm not going to show you. It's fairly simple though. And again, you have, this denotation is essentially one-to-one translation with the implementation. Okay. Right, and we keep going. We do approximate contains of convex polygon and a point. Right, so we expand the polygon again by the tolerance value. And then we check that the point is inside all of that. But we know that that point is really just one point, so this isn't really subset or equal. We can kind of just say is an element of right here. And that's really just simplifies down to distance. So you're just checking that the distance between the point and the polygon is less than the tolerance, or less than or equal to the tolerance, which we just implemented. So we just use that, and again, it's just one line of code to see if a convex polygon contains a point. Okay. Right, so approximate containment, this seems like a step up now. We're checking if a polygon approximately contains another polygon. So what we do is we reason about this a little bit. We know actually that when we create this expanded set, that the new set is still convex. So I hope you remember the definition of convex, but I put it up here for you to remember. So what it means by convex is if we pick any 2 points inside of this new area, then the line segment between those 2 points are still going to be in the set. And what that means is if we just consider the vertices of set B, of the polygon, and we check that they are inside set A, now we can infer that all of the points between those points are in the set A. So the entire boundary of the polygon is inside this area already. And it's fairly easy to see from there that at any point inside the polygon, you can just kind of draw a line in any direction and find 2 points on the boundary, and then fill in the whole polygon. So you can imagine kind of a line just scanning up and like getting all the points of the polygon. So really, what this means is just by checking that the vertices are inside of the expanded area, we know that the whole polygon is inside the expanded area. Okay. Which makes the implementation extremely easy because we just do approximate contains polygon of the vertices of B. Right? Any questions about that? Right, so, sorry, one second. So we have approximate contains of convex polygon, convex polygon. So let me just think again back to our pathological case. I hope you guys remember this. Does it mean that they're equal now? And now that we've defined all these denotations and we've defined what it means to be equal, we can think in terms of those denotations, and we can actually look a bit closer, and we can say, again, we're just expanding one and checking if it's inside, and then checking the other way around. And we actually can see in this case that now, this pathologic case, we can say definitively that it's equal, which is something that we couldn't do before, and you might be arguing with your colleagues about. But now that we have this framework, it's very easy to say that it is in fact correct that they are equal, okay? Which is one of the key points that I want to get across to you. Right, so how do we actually go about approximate equality of convex polygons, which is the question that I asked at the very beginning and said we'd be solving. So let's go ahead and try and do it. Instance approximate equal of convex polygon, where we don't actually need to implement it because there's a default implementation, so we've implemented it in 0 lines of code. Thank you. So that's the end of my talk. Thanks, guys. Cheers.
Great, we've got plenty of time for questions. Well, I guess I have a quick question. This all kind of fell out nicely of having a denotation of like a list of points, but what if you used a different denotation for what a convex polygon was?
Right,
It
yeah.
seems like you just got very lucky at the start almost.
Right, yeah. Well, I mean, it's important to note that what representation you use, so what you're actually using in your code, isn't so important, right? It's as long as it's as long as you have some practical way of relating it to the denotation, that's what's important. So you can go back and you can find some other alternative. You could pick a set of half spaces, like a literal set of half spaces, which is sort of, again, close to the denotation. But you could do it, you can change it to whatever representation you want. As long as it fits the denotation, all the functions should still do what they do, and you'll get the same design in the end if you pick the same denotation for it. Yeah.
Thank you.
Okay.
Any other questions? Nope. Cool. Well, let's thank the speaker again.
Great. Thanks, everyone. Cheers.